Hi, and welcome back to our discussion of water vapor in the atmosphere. And what we're going to do now is talk about water vapor variables, moisture variables. So we've got a whole list of those to go through. Some of these you've probably seen already, some you may not have. We'll discuss these in detail. First off, dew point. Dew point, more or less, is the temperature that air has to be cooled to reach saturation. Now, while you're doing that cooling, you're holding the amount of water vapor in the atmosphere constant. In other words, you're not taking water vapor out or adding water vapor to the air. The amount of water vapor, the water mass, is constant, and you're just cooling the air. So this is a true measure of the amount of moisture in the air. And it tells us the actual amount of water, not how much could be there, but the actual amount of water. Whenever you want to do a calculation of the actual amount of water vapor in the atmosphere, you always use the dew point. And looking at a saturation vapor pressure curve, we looked at these already. We talked about the equation for this curve. We said it was exponential. We calculated this using Teton's formula. But everywhere along that curve, that red line, is saturation. Now, we talked earlier about there are times, or almost always, in the atmosphere the air is not saturated. You have some actual amount of water vapor in the air, and it's less than your saturation amount. So let's look at some particular temperature, T, in our atmosphere. We're going to call that T atmosphere, and that's the green T, or the green lines that you see there. The actual amount of water vapor is that green dot at a particular temperature T. And at that particular temperature, you could have a lot more water vapor in the atmosphere. You can have, as that arrow indicates, all the way up to that red line. In this case, our atmosphere is subsaturated. Saturation amount is on the red line, and the actual amount is that green dot, so you can see that we're subsaturated. So if we want to reach saturation, what we'll do is reduce the temperature while holding the water vapor pressure, or the actual amount of water vapor in the air, constant. So reducing the temperature, we call that isobaric cooling, because the pressure of the water vapor is not changing. So if you cool the air, you're moving horizontally to the left until finally that green dot moves down to intercept, moves over to the left to intercept that curve. And at that point, the temperature is now equal to the dew point. It's a colder temperature, and we've reached saturation. So at that point, where the actual amount of water vapor is equal to the saturation amount on that red curve, that's where you have 100% relative humidity. The frost point is similar to the dew point, except it's just with respect to ice instead of with respect to liquid water. Remember, we said that frost or the ice saturation is lower than the water saturation. We covered that last time. And this is always temperatures less than 0 degrees C. You don't have frost points warmer than 0 degrees C. Another moisture variable is the wet bulb. The wet bulb temperature is the temperature which you have to evaporate air, or evaporate water into the air under constant pressure to reach saturation. And the wet bulb is not the dew point, of course. They happen two different ways. With the dew point, we cool the air to reach saturation. In other words, we held the amount of water vapor in the air constant. Here, what you're doing instead is you're adding water vapor to the air. If you're adding water vapor, then the vapor pressure is increasing. You have more water mass in the air. But at the same time, when you evaporate something, just like when you get out of the shower in the morning, there's water on your skin, it evaporates, and it takes energy. It cools the air. So the temperature decreases, but you're adding water vapor. So if you're adding water vapor, you're going up on this curve, you're going straight up. But if you're cooling, you're going straight to the left. So it's a combination of the two, so you're going at an angle towards that red line. You're cooling and adding water vapor, and that's what wet bulb is. So water vapor is added to the air by evaporation, and the energy for evaporation comes from the air, and it decreases the temperature. Okay, so that's wet bulb, but there's a couple other terms we need to go through. Absolute humidity is the mass of water vapor in a given volume of air. So looking at the air and looking at the water vapor, if you can remove the water vapor and still have it in the given volume of air, the mass of water vapor in a given volume of air is your absolute humidity. And absolute humidity is more or less the density of water vapor in the air. It's the mass divided by volume. The mass of water vapor divided by the volume of air. Usually measured in grams per cubic meter. And the problem is when volume changes, the mass doesn't, so your absolute humidity changes. So that's not a real good measure, absolute humidity. So we have to come up with something that doesn't change with volume, because in our atmosphere, as air goes up through the atmosphere, the volume increases and the absolute humidity changes. So we've come up with a couple other terms that are a function of mass. One of them is specific humidity. And specific humidity is the ratio of water vapor in a parcel of air, the mass of the water vapor in a given parcel of air, to the total mass of air in the parcel. So in other words, take the ratio or divide the mass of water vapor divided by the total mass of air. Now, as you know, water vapor is a very small percentage of the air, usually only 1%. So the numbers that you're going to get when you take the mass of water vapor and divide it by the total mass of air is going to be on the order of 0.01 or 0.001 or something like that. In other words, it's going to be very, very small. So that's something that you should remember when you do these calculations. Here's just the equation for it: specific humidity, mass of water vapor divided by total mass of air. We use the symbol Q, and usually it's measured in terms of grams per kilogram. If you just take one divided by the other, grams divided by grams, it'll give you a number of like 0.001. But when you look at it in terms of kilograms of dry air, then you're going to have more water vapor, bigger numbers. Nice thing is specific humidity doesn't change with volume. As it expands, the mass is the same, the ratios are the same. So specific humidity doesn't change with volume. Mixing ratio is very similar to specific humidity. The only difference is, instead of looking at the total mass of air, we pull out the water vapor molecules out of the air, and we divide the mass of water vapor divided by the mass of dry air. So it's a little bit different. In the previous and specific humidity, it was the total mass of air, not just the mass of dry air. Here's the equation. It's a ratio, and we use the symbol W. And when you divide one by the other, once again, you'll get a very small number. But if you want to put it in terms of kilograms of dry air, you have to multiply it by 1,000, and you'll get something like 1 or 2 grams per kilogram. And of course, that does not change with volume. There are some numbers for you. Dry air, typically 1 to 2 grams per kilogram. Tropical air, somewhere around 20, just to give you some perspective. We put it in terms of grams per kilogram because meteorologists don't like to talk in terms of really small numbers. We don't say that it's 0.02 grams per gram. We like to use whole numbers. That's why we multiply it by 1,000. And here's some equations for you that you can use, how to go from mixing ratio to specific humidity and back and forth. Remember that the mass of dry air is usually much bigger than the mass of water vapor in the atmosphere. So as a result, your specific humidity is going to be really close to mixing ratio. And here's some other equations you can use to calculate the mixing ratio based upon the water vapor pressure in the air and atmospheric pressure. And also you can calculate specific humidity from mixing ratio. The last thing we're going to talk about is relative humidity, and basically relative humidity is the ratio of water vapor pressure, the actual amount of water vapor in the air, divided by the saturation, or how much could be in the air. The actual, we usually use dew point to calculate that. Saturation amount, we use the air temperature. So that's how you get the two different pressures and you get the ratio. The World Meteorological Organization uses a different definition. It's the actual mixing ratio divided by the saturation mixing ratio. And that's all I have for this video.